Alright, let's explain what a limit is. So limits are useful tools in addressing continuity. And continuity is basically a point that will exist on a function. So we know that a continuous function is a function that we can draw out without lifting our pen, right? Like an example of a continuous function, the function on the left is a quadratic function. A linear function is an example of a continuous function because I can draw it without lifting my pen. And all of these points, there are no breaks in the function. Okay. Now, a limit of a function can be defined as limit as x approaches a of f of x will equal L. So this is going to be the general template that we're going to use to express what a limit is. So how this reads out in English is basically as x approaches or equals or becomes a, f of x or y will approach a value L. Okay. Now, as long as L is a finite number, then the limit will exist. And a finite number means it's a constant, it's a fixed number, it's a number that actually exists, right? If L is infinite, so what that means is it could either be plus minus infinity, then the limit does not exist. Okay, and we'll look at cases where the limit will exist and where the limit won't exist. So in this case, as x approaches a, f of x or y will approach L. And let's take a look at one of these points on this graph here. So if I look at the limit as x approaches 1, right? So if you're looking at as x approaches 1, f of x, and let's call this function f of x here, right? When x becomes 1, f of x also will become 1, right? So f of x will approach 1, right? So that's basically the premise of a limit. But you can also look at limits from either side of the point x is equal to a, right? Like for instance, if I was looking at limit as x approaches 1 from its very left, right? So what that means is basically I'm looking at approaching 1 from the left, and 1 from the left is a really small value that's close to 1. So 1 from the left can be like equivalent to like 0.9999. So it's a value very small and it's very close to 1 and it's approaching 1 from the left side. So if I look at the limit approaching 1 from the left side of f of x, then you can see that it gets closer and closer to 1, right? You can also take a look at a limit from the very right of a point A. So this is the point A. We can also look at a limit from the very right of point A. So basically we're looking at the limit as x approaches 1 from the right side. And if you're looking at 1 from the right side, it's a value that is really close to 1 approaching it from its right. So that could be like 1.00001, right? And if you looked at the value of f of x, you can see that you're basically approaching this guy from the very right. Basically this will also get closer and closer to 1. Okay. When you're looking at a limit from either the left side or the right side, this is what we call the left or right-handed limit respectively, right? So a left-handed limit in the case of a left-handed limit, we're basically looking at a value of a of f of x from the left side, right? A right-handed limit, so I'm going to write it right here. You're looking at a value of x, in this case a, from the very right of f of x, right? And we test the left and right-handed limits in conjunction with the actual limit to see if the point exists. So all of these three things are going to be related. I'm just going to, right? So all of these three things are going to be related, and this is going to show if a point is continuous, right? So the general limit properties show if a point actually exists on a function. And I'm just going to erase this, make some space here. Well, I shouldn't erase that. Okay. So the general idea, if a point does exist, is if the left-handed limit of a function is equal to the right-hand limit of a function, and this is equal to some kind of finite value, this is the first criteria to show that the point x is equal to a is continuous, right? But the second criteria here is that all of these two things here, the left-handed limit and the right-handed limit of f of x, should also equal to the limit as x approaches a of f of x, so the original limit, right? And when you look at the limit as x approaches a, you're basically looking at f of a, which should equal L, right? So collectively, these three things, the limit as x approaches a from the left side of f of x should equal to the limit as x approaches a from the right side of f of x, which should equal the original limit as x approaches a of f of x, and in that case you should get f of a, which is equal to L. Now this is basically the general way you can test to see if a point actually exists on a function. I'm going to show you guys how to do this by looking at this graph, right? This seems really confusing when you're looking at algebra, but I'm going to kind of relate this idea to this graph to show that a single point will exist, right? So let's say that we wanted to show that the point -2 and 4 is continuous. So we're asking ourselves, is this point continuous? Right? And you can just look at the graph and you can tell that, yeah, it does look continuous, but I want to prove this using limits, right? So to show this using limits, I'm just going to erase this just to make some space. To show this using limits, first thing we need to do is we need to test to see the left and right-handed limits, right? So because I'm looking at this point here, okay, I'm going to start with the left-handed limit, okay? So the left-handed limit here, limit as x approaches -2 from the left side of f of x. So as x approaches -2 from the left side of f of x, y, or f of x, will approach. So you're basically approaching -2 from the left side. -2 from the left side could be like -2.00001, right? It's a really small value that's to the left of -2. And you can notice here that it's getting closer and closer to 4. So as x approaches -2 from the left side, y will approach +4, right? And you can do this because all of the points are joined by a line or a curve, right? So the value gets closer and closer to 4. Now let's take a look at the right-handed limit. Limit as x approaches -2 from the right side. So for each value of a, you have to test the left side and the right side limits. Okay, so as x approaches -2 from the right side, f of x, or y, will approach. And basically what we're going to be doing here is we're approaching -2 from the right side. So you're getting closer and closer to -2. And -2 from the right side can be a value like -1.9999. Right? So it's a very small value that's to the right of -2. And in this case, you're going to get a similar value of 4. Right? It gets closer and closer to 4. We can also understand that the original limit here, the original limit as x approaches -2, when x does approach -2, we can notice here that f of x will basically become f of -2. And we know that at -2, we're going to have the value 4, right? Because f of -2 is equal to 4. This is going to be a limit property that we'll discuss later when we're solving for limits. But f of -2 is equal to 4. So we can see that the left-handed limit, the right-handed limit, and the original limit are equal, and they're equal to a finite value, which is 4, and they're all equal to each other. So because of that, we can make this resulting statement, therefore the limit as x approaches -2 from the left side of f of x is equal to the limit as x approaches -2 from the right side of f of x, which is equal to the limit as x approaches 2 of f of x, which is equal to 4. And this proves that the point x is equal to -4 is continued, and x is equal to -2 is continuous. Sorry about that. Right? So this is a way we can prove a point is continuous or not by using limits.